Hey guys, welcome back to the second part of this recorded lecture. And yes, I did have a change of attire and I also changed location. Don't even worry about it. But in any case, so we're just gonna continue with our recorded lecture here. This time we're going to be taking a look at gaseous fuels, case 2, example number 2. Okay, I'm sure you've already downloaded the transcript. Oh, well, at least I hope you did. In any case, you might think that it's a bunch of gibberish or whatever. It's a mess. I can see that much. I'm sorry if it's a bit nonsensical, but don't worry. I'm here to make sense of that. Okay. Hopefully you're also watching this ahead of time because again we have a recorded lecture. Sorry, a live discussion right after this. So hopefully you're already watching this ahead of time. Um, but in case we don't have a live lecture, I should have announced it somewhere. So sorry if there's some confusion. Just uh, take that announcement. Well, if I did announce anything. So in any case, let's take a look at the problem first. So ORSAT analysis of the snap gas from the combustion of a gaseous mixture of acetylene and methane shows 9.82% CO2, 1.37% CO, 0.69% H2, 5.34% O2, and 82.78% N2. Right? And then determine A percent excess air, B mole percent composition of the gaseous fuel, and C cubic meter of wet air supplied at 26 degrees Celsius, 765 torrs, and 70% RH per kilogram of fuel. Okay, so among these required values, I think the new one should be letter C. I'm not sure if I've already discussed this since like I mentioned before, I'm recording ahead of time. But in case that this is new, so we're going to be introducing a new concept this time around. Uh, but it shouldn't be a new concept. I think it should have been discussed in chemical engineering calculations 1. This is in regards to saturation pressure of water, but we're gonna cover that later on just to touch upon it. Okay, but in any case, so let's go ahead and solve the problem. So let me just switch to the whiteboard screen here. Okay, well, now like the other problems that we already solved before, we're going to start off with our given. Sorry if I'm jumping right into this. I just want to make sure that this would be under 30 minutes since in case you're just watching this on our scheduled date. So just want to make sure I'm going through this as fast but also understandable at the same time. But in any case, so we're drawing the given. Again, it's just a free body diagram. So we've been through this numerous times before. But in this case, we're given acetylene as well as methane. So this is where your knowledge of organic chemistry comes in. Hopefully, you still remember a bit of it. It should have been discussed back in general chemistry. What acetylene means. Acetylene basically is acetylene. Sorry, acetylene or ethylene. So that's gonna be C2H2, right? And then methane is CH4. Okay, and then we're also given our composition of slack gas, which is 9.82% CO2, also given 1.37% CO, 0.69% H2, 5.34% O2, and 82.78% N2. Right. So the first thing we have to do always make sure that the given percentage of the product gas is 100%, especially for case 2. Okay. Again, we can find out if it's case 2 if there is a given on the right side or on the product side of our combustion reaction. So if we actually total this, we're going to reach 100%. So that means the full ORSAT analysis is given to us. So we don't have a missing water or anything else that's missing. So we can immediately jump right into answering the problem. Okay, so moving on, first thing you have to do to solve this is, of course, place a basis or add a basis. Again, for case 2, it's always best to have a basis on the product side. So that's going to be a basis of 100 kilomoles, just to make the calculations that much easier. So kilomoles of dry stack gas. Again, it's imperative that you use dry stack gas because this is an ORSAT analysis. So if you say it's 100 kilomoles of stack gas, then you assume that this is not an ORSAT analysis, but rather a complete analysis. Okay, so it's very important to get right into that practice, especially if there comes a time that there is water, so you're gonna know the difference immediately, or at least know what you have to do. Okay, now, like the previous problem, example 1, what we can do first is, again, do our supplied N2. This is totally up to you. If you want to start with your atomics, that's completely fine. Again, the only reason why I used supplied N2 before was just to show the flow of case 2. Okay? Alright, well, we're just gonna do that again. So we're going to use supplied N2 just for a bit of consistency. So the transcript may be different, but I'm sure you can still understand it, since I think I did atomics there first, but it shouldn't make too much of a difference uh, answer-wise. In any case, our supplied N2 would be 82.78 kilomoles. Again, since we don't have nitrogen in our fuel, the supplied uh, or the nitrogen in the product gas is also equal to our supplied N2. This is just a reminder, the supplied N2 is only equal to the N2 in stack gas if there is no N2 or nitrogen from our fuel. Okay, I'm sure I should have discussed that before, but I just want to reiterate that point. Okay, well, in any case, we can proceed right on to the others. So we have our free O2. So our free O2 is given here, which is 5.34. Right? And this should be equal to our excess O2. But since this is incomplete combustion, we have our CO and we have our H2. We have to add those up. So this is plus CO over 2 plus H2 over 2. Okay, so substituting the values of CO over 2 and H2 over 2, and then just transposing them to the other side, we can get our excess O2. I'm not gonna show that fully, okay? But you should be able to understand that we just substituted the values of CO and H2 and then just move them to the other side. But in any case, so we get our excess O2. This is 4.31. Alright, next thing that we can do for the product gas is our atomics. So in this case, we can do our at C, which is just equal to our CO2 plus CO. This is 9.82 plus 1.37. Okay, so adding this should be 11.19. Alright. Okay, so now that we have our excess O2, we have our at C, and we have our supplied N2, remember again that what we can do here is to get our theoretical O2 using our supplied N2 and our excess O2. So let's just do that again. So supplied N2, this is 82.78. Please remember that this is equal to supplied O2 and supplied O2, or sorry, supplied O2 multiplied by their molar ratio of 79/21, and also supplied O2 is equal to our TO2 plus our excess O2, which is 4.31. Now multiply that by their stoichiometric ratio, that is 79/21. Now we can get our theoretical O2, which is 17.69 kilomoles. Alright, so now that we have our theoretical O2, we also have our excess O2. We can immediately get our percent excess air. So that is one of the requirements. It's actually the requirement for letter A. So let's just get that right now. So for letter A, to get percent excess air, okay, we just need to divide our excess O2, that's 4.31 over our theoretical O2 of 17.69, then multiply this by 100 to get our percentage excess air. So we should be able to get our percent excess air to be 24.36%. So this is our percent excess air. Again, for case 2, it's very easy to get percent excess air. If you can actually if you can actually see, we can already get that just by getting our excess O2 and our theoretical O2. We don't have to get our atomic C first, but getting atomic C is fairly easy as well, especially if the carbon dioxide and carbon monoxide are already given. Okay. Well, in any case, that should be it for letter A. For letter B, we're going to get the mole percent composition of the gaseous fuel. So for these, we have to do a table. But before we do that, we're still missing one thing from our table, and that would be our at H. So we're just going to do that first. Let me just clear the board. Okay, so we're proceeding now to letter B to get our mole percent composition. But side note, good news, I have new markers. They're much finer, so we should be able to do this a bit neater, or hopefully that's what my intention with getting these markers. But in any case, so now we have to get our theoretical, our at H using our theoretical O2. Again, if you can remember, let me just erase this again. So we get our theoretical O2. This is equal to our at C plus at H over 4. We already have our theoretical O2 as well as our at H, wherein our theoretical O2 is 17.69 and our at C is 11.19. So plus at H over 4. Okay, rearranging the formula, we can get our at H. And our at H here is equal to 26. Alright, so these two atomics are the only components of our fuel. We only have carbon and we only have our, as well as our hydrogen. So we don't have nitrogen, sulfur, and oxygen. So we can get right on ahead to making our table. So that would be our C2H2 acetylene, our CH4, then the number of moles. So the number of moles both are unknown, so that's actually what's being asked, the mole percent composition. So like our previous problem, I'm not sure if there is a previous problem like this, but this may be the first, but just in case, I'm just gonna say that. So this is gonna be, we just have to assign C2H2 as X, and we can assign CH4 as Y. So obviously, you can use any notation that you want. You can use A, B, C, D, whatever you want, as long as it helps you solve the problem much easier. But in any case, let's proceed to filling up the rest of the table. Wherein our at C, we'll just do the same thing for case 1, wherein we multiply the subscript by the number of moles. So for at C of acetylene, this will be X times 2, which would yield 2X. As for CH4, this is Y times 1. So remember that if there is no subscript, that is always 1. Okay, so don't ever forget that. That is not 0. So this is Y. So, or 1y if you want. Uh, and then we do at H, the same thing for acetylene, it's 2x. But for methane, this would be 4y. Okay, so now I think you should have a fairly good idea of what we're trying to do here. So we have our at C. We already know the value of our at C to be 11.19. And then for at H, this is 26. So basically, we have here our two equations, two unknowns. So we have the first one, for at C, it's 2x plus y is equal to 11.19. Then we have our at H, 2x plus 4y is equal to 26. So obviously from here, you can use your calculator. There should be two equations to unknowns in your calculator, but if you want to do it manually, that's fine as well. It's already fairly simple here. You can just subtract this and then just divide the remainder. This should be negative 3y divided by whatever 11.19 minus 26 is. And then you can get x and y. No matter what the method, you should be able to get for x, this is 3.13. Then y, this is 4.93. Okay, let me just erase this. So as for the values, it's very um, helpful, or I guess uh, it's very assuring or reassuring if you check the actual values. So if you can check the transcript, I actually have an erasure there. I think I entered a wrong value somewhere along the lines where I was using a calculator. So um, it didn't work out when I tried to plug them into these formulas. So make sure you do that as well. But if you're really confident that that is the right answer, then go ahead. But this is just a piece of advice, since it doesn't really take that much of a time. Just try to plug in the values just to make sure. Okay? Well, in any case, since we already have the number of moles of acetylene as well the number of moles of methane, we can immediately get our percentage mole composition for each of them. So, how can we do that? As for C2H2, we just need to divide its number of moles by the total. So our number of moles of acetylene is 3.13. And the total, we just need to add acetylene, which is 3.13, plus our methane, which is 4.93. Then, since this is percentage, we multiply it by 100. So for acetylene, we should get 38.83%. Okay? Then, of course, for percent CH4, if you want, you can still do this. Divide its number of moles by the total, or you can just subtract 38.83 from 100%. Since there are only two components, you can do that right away. So if we do 100% minus 38.83%, we're going to get 61.17%. So these are our percentage mole composition. Okay. Alright. Well, now we're moving on to letter C. So it's very easy. Let me just do a quick recap. So it's very easy to get the percentage mole composition. Just do a table. So this should work even though there are three components of the fuel. Normally, if there are three components of the fuel, there is another unknown. Could be most O2, or could be at N, could be at S, whatever the case. So don't worry about that if that's what you're wondering. I'm sure we're gonna have an example of that later on, or in other types of fuels. But right now, it's very easy if the fuel is just binary, or there are only two components. But in any case, so now we're moving on to our letter C, which is a bit different on how we solve it. Since there are, or since for letter C, it's asking for the cubic meter of air, cubic meter of wet air to be precise, over the kilogram of our fuel. So in this case, since uh, the problem reiterates or says that it has to be cubic meters of wet air, and then we also have the percentage RH, we actually have to get the number of moles of water first in the air. So we do that using by utilizing the saturation pressure, which is, if you can remember, that is PS. So PS, or saturation pressure. So I'm not sure if was discussed in chemical engineering, sorry, chemical engineering calculations 1, but basically there is a formula to solve PS. There is also a graph, a psychrometric chart, if I can remember correctly, where you can get PS right away just by plotting it using the percentage RH as well as the temperature. But in the case of chemical engineering calculations too, what we do is actually calculate it using a specific formula. So that's the green text that you see in the transcript. It's very long, and I expect you guys to actually memorize that. So I've been trying to, well, not trying to. I asked that with my previous courses as well, since it's also one of the few formulas that you actually have to remember in chemical engineering calculations too. It's pretty simple once you get the hang of it, especially if you review on your own as well. So hopefully you can remember this before we have our quiz, which should be next week, I think. But in any case, for right now, let me just write the full formula. Not sure if just it is gonna fit in one line, but this is exp. So exp is basically e raised to 73.649 minus 7258.2 over t, then minus 7.3037 ln of t plus 4.1653 times 10 raised to negative 6 t squared. Okay, it's fairly long. Well, not actually that long, but there are just a bunch of components, but they're very easy to remember, especially if you, again, try to review on your own. On the transcript, you're gonna see they're multiplied by, this PS is multiplied by 760 over 101,325. That's actually because this formula is used to get PS in terms of kilopascal, or sorry, not kilopascal, but pascal. So that's why there is a conversion of 760, which is mmHg or torrs, and then we're dividing it by 101,325, which is in terms of pascals. So in this case, we're also gonna do that. So that's because our pressure is given in terms of torrs. So that's 765 torrs. So what you have to do here is actually just to plug in the temperature. So the temperature that we have is 26 degrees Celsius. So that 26, we actually have to convert that into absolute. So we have to add 273.15 to make it Kelvin. Okay, so this has to be absolute unit. You may get a different value of PS than what I have. It's because I'm using a calculator which is automatically calculating the PS. Since that is much more accurate since it's exact. These are actually rounded off already, but this is fine, still fine. There should only be a minimal difference, usually just decimal points, and that is completely fine. But in any case, we are going to get PS here, which is 25.2 torrs. So that's 25.2 torrs. And now, how do we use this saturation pressure? Hopefully, this has been discussed in your chemical engineering calculations 1. What we have to do is actually utilize the formula of pH2O over the pressure of dry air is equal to NH2O over the moles of dry air. So I'm not sure if you're familiar with this formula, but basically it's just utilizing uh, the number of moles as well as pressure. This should have been discussed on your chemical engineering calculations 1, but if not, it should also have been discussed in your um, general chemistry or chemistry for engineers. This is actually Reynolds law, which is utilizing the pressure as well as the um, mole ratio of the gases. But here, if you can see, we already have our NH2O. We just need to manipulate the formula in order to get our NH2O. So in this case, if I'm not sure if you can remember or if it's already been discussed, pH2O, in order to get that, we actually have to utilize our PS, where in pH2O is equal to our saturation pressure times our percentage RH. Okay, so we're gonna do that. Let me just clear the board again. Okay, so now we're utilizing that formula. So let's rearrange it first. We get our NH2O. This would be equal to pH2O over our pressure of dry air multiplied by the number of moles of dry air. So now we have our pH2O. Again, it's equal to PS times RH. So our PS is 25.2 torrs. So let me just write that. So torrs multiplied by our relative humidity, which in this case is 70% or 0.7. As for pressure of dry air, we don't actually have that, but if you can remember, the pressure total of a gas is basically just the pressure of its components or the sum of the pressure of its components. So that's just going to be pH2O plus the pressure of dry air. So that's the pressure total. And we already have our pressure total since it's given, that's 765 torrs. We also have our pH2O using the formula for PS. So if we rearrange this formula, we get for pressure of dry air, it's going to be pressure total minus pressure of H2O. So let's divide this. So that's going to be 765 torrs minus our pH2O, 25.2 torrs multiplied by 0.7. Okay, and then we multiply this fraction using the moles of dry air. So how do we get the moles of dry air? Basically, we just use the supplied N2 and add that to our supplied O2. Or if you want, you can also just utilize the molar ratio of supplied N2 to get the moles of dry air. So let's do just that since we already have our supplied N2. Our supplied N2 is 82.78 kilomoles. Then in order to transform this or change this into our moles of dry air, we have to utilize again the molar ratio, which is 100 for, of course, the air, divided by the molar ratio of 79 of nitrogen, which is 79. Okay, hopefully you're still following along. If you have any questions, please make sure to write them down somewhere and then post them on the discussion. Or later on, if you still have some time in our live lecture, I'm going to answer them live as well. So hopefully you're still following, but in case you're not, don't worry about it. We're going to try and discuss that whether it be live or through the offline discussions. But in any case, we're already going to be able to get our number of moles of H2O. So in this case, let me just see where it is. The number of moles of H2O is 2.47 kilomoles. Again, if you're using a different PS, this is going to change a bit, especially if you plug in the formula. or plug in the value of T on the formula I provided earlier. But if you notice, it shouldn't make that much of a difference. Could just be 2 point something, 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 whatever. But it should still be fairly close. So that's absolutely fine. But again, we're going to be able now to get our cubic meter of wet air. So we should have been able to discuss this on gaseous fuels case 1, wherein the cubic meters of any gas, we just have to use our ideal gas equation. So this is divided by our kilogram of fuel. Let's not forget about that. So the cubic meter of air, again, this is nRT over P. So our N, again, we just have to use the supplied N2. So it's 82.78 times 100 over 79. Of course, if you want, you don't need to use this. You don't need to use this method of computation for the moles of dry air. You can immediately just get the moles of dry air and plug it in here. But I'm just trying to save space on the board, so I don't calculate all of it. But basically, you should get the gist of it. Uh, but in case you're not, or in case there are any uh, misunderstandings or there are things that you don't understand, please feel free to always ask me about it, okay? And also, again, I hope you're also trying to study on your own, especially these times where I'm not always going to be available or you can't always, find me. But I'm always going to be trying to be there for you guys just to make sure that you're learning everything that I want you to learn. But anyways, so this is our most of dry air right now. Again, we need the most of wet air. So that's why we got our most of H2O. So we just add that. That's 2.47. So these are both in terms of kilomoles. And then again, we just multiply this by our RT and divide it by our pressure. So this is 8.314. Sorry, that's 8.314 multiplied by our temperature, 26 plus 17. This is over our pressure of 765 multiplied by 101.325 over 760. So this multiplication is necessary because again our R, or universal gas constant, is in terms of kilopascal cubic meter per kilomole Kelvin, and since 765 is in terms of torrs, we need to convert that into kilopascals just to make sure that the uh, units are cancelled out. But this should be our cubic meters. So now we just need to divide this whole affair by the kilogram of fuel. So our kilogram of fuel, we just need to use the number of moles that we were able to obtain earlier. So that's for acetylene, 3.13. So this is in terms of kilomoles. So let me just do the units here. So in order to cancel this out, in order to make sure it is in terms of kilograms, we just need to multiply it by its molar mass. So acetylene is C2H2, so that's 24 plus 2, that's 26 kilograms over kilomoles. And then for our methane, that is 4.93 kilomoles. Multiply this again by its molar mass, so it's 16, right? Yeah, 16. 16 kilograms per kilomoles. I'm not gonna write the unit. And this is 16.32 cubic meters per kilogram. So this is our cubic meters of wet air per kilogram of fuel. Alright, well, that should be it. But we're also going to have a live discussion later on just to reiterate everything and then to answer all of your questions as well. But right now, I also want you guys to give a feedback on the recordings that we have here as well. So, of course, I want to have the quality improved. But since I moved, I think there's a bit of reverb here, a bit of an echo. So if you're hearing that in this video, hopefully you guys tell me. I just don't add it in the discussion. Please message me directly using the Canvas chat, or if you want, you can email me or just leave it in the comment in the YouTube video if you want. But in any case, that should be it for this example number 2. But in any case, I'm gonna see you guys later for our live discussion. But for now, see you.